So, I'd like to get us on the same kind of wavelength, so we're talking about the same thing. So when I say extreme temperatures and extreme conditions, this is really what I will be referring to. Um, so the two types of main extreme environments that I see is very hot, very arid desert environments. And also we have very cold, very slippery, freezing environments. Now, the desert environment is one I was exposed to in the Middle East, also in India. There was a very dry, arid climate at that location also, and then also in California, parts of California. So you get the highest temperatures during the day, very high. The instrument can sometimes struggle in the heat because it's not designed for very hot temperatures, 40, 50 degrees Celsius, any kind of electrical device will start to struggle. And in India, we saw, upwards of 50 degrees Celsius. Even in California, I've seen highs as 110, 120 Fahrenheit, 40, 45 degrees Celsius. And the instrument really struggles. And it also struggles if we leave it in direct sunlight at the same time. So a little bit more on how we can get around some of those problems. The user will also feel fatigue, okay, because it's very hot, and also they have very large amounts of personal protection equipment on. So it's a very difficult environment where the user and the instrument are struggling. I've heard that the temperature sensor also fails. So we're sticking to the back of a very hot panel and it can fall off repeatedly just due to moisture buildup where the suction cup is. So we're going to cover how to mitigate some of these problems. But the biggest in a desert environment I found is high amounts of dust because the panels are consistently soiled. It's causing very bad connections where dust is getting inside the connections, which can cause internal arcing. I'm not just talking about the MC4 connections of the solar PV array, but also the connections into your unit. So if you look at the top of the PV210 or of any of our units where the cables are going to be connected, we don't want dust and dirt inside there because that can cause problems later on. So it is key to keep your instrument clean. And again, we're going to cover how to mitigate all of these problems in more detail. Well, I say mitigate and notice that because we can't solve them, unfortunately. Just lessen their blow on our working day. So with a freezing environment, we're working often below freezing temperatures, particularly if you look at the polar vortex, which is happening here in the United States right now. A lot of the northern states, the Midwest, have been really hit hard. Chicago is going to have Arctic temperatures. Now, it's not always that bad, but definitely in that part of the country, it does get very, very cold. So last year I was in Minnesota and we were having a problem where a client's instrument wasn't working for him. He would get it out of the truck and he would start it up and it would have problems. So the reason was he was storing that below zero. Okay, he was storing that below freezing temperatures. So again, his instrument's not going to work very well in this environment. He also feels more fatigue. You're expending more energy when it's cold to keep yourself warm. Again, temperature sensor falls off because it's just too cold. There's too much moisture. High amounts of snow, meaning the panels are consistently soiled. And again, I haven't put can cause bad connections because bad connections would be caused by bad workmanship, really, in a freezing environment. But it can, if you do have water ingress, it'll cause ground faults, etc. Now, when we look at both of these environments, they offer us very similar problems. We just have to deal with them in slightly different ways. So the next part of the presentation, what I'd like to go through is just explore some of these environments more and some of the problems that come out and what we can do to fix some of those problems when we're using our test device in the field. So I actually went out to the community and I asked for some feedback. And one of the interesting points I got was from Hamza, a gentleman who's based in Saudi Arabia. And he said to me, August 10th, ambient temperature is 52 degrees, that's Celsius. Module temperature definitely way above 80 degrees, but we can't hold on to the modules nor the tools. And mind you, it's not even 10 a.m. The real challenges are trying to test the strings at noontime under the hot aluminum structure to find untied connectors. So he's talking about a real world physical problem there that I've described on the previous slide, that it's just too hot to work, can't get underneath the panels to look at the cables. This is a real big problem. And unfortunately, when we have extreme heat like this, there's not really much we can do to mitigate the problem. I would just advise using, the right personal protection equipment. Avoid touching the aluminium or the aluminum structure to your skin, which will definitely burn. But one of the bigger problems I've found in this sort of environment, rather than the heat, and I would like to stay on this topic for a little while, is module cleaning and what dust does in this environment and how it can really affect our test results. So to put you in the picture, this is the Mohammed Al Bin Raktoum solar farm in the United Arab Emirates. And a user was having difficulties operating our device in this environment, so I flew out to see him. So you can see one thing we did to mitigate the heat on the right-hand side, where we're testing underneath the panels. So this problem that Hamza had of it being very hot, this is likely because this was on a rooftop. So use your environment to your advantage and keep the unit under shade and yourself under shade whenever possible. Now, I came to the panels and they were absolutely covered in dust because we're in the middle of a desert, an arid environment. So I have a video for you now, which I'd like to show you, of us trying to clean those panels. So you can see by the video that we're really moving the dust around. There's no real way to clean them very, very thoroughly, certainly within a short amount of time. So, and also in this environment, there is not much water to clean the panels. So this was a real problem for us in order to get any accurate test results, as you can see from these extreme conditions. So we needed a solution to this. So if we can't clean, what will happen is dust will build up and accumulate over time, and this aggravates the soiling effect. The dust layers can be very dependent on your environment and your location. For instance, if you're near a roadside, or you are in kind of this more desert, arid area, if there's a lot of wind, that can have an uplift on dust onto the panels. All of this can increase the dust buildup. And you can see from this picture on the right-hand side here, this is another example in California. And you can see I've cleaned away some of the dust here on the left-hand side of the panel. You can see how dusty the other parts of the panel were. So when we're testing in extreme conditions like a desert, then I think the biggest problem you have is dust, because we can mitigate heat by rotating our staff, by making sure people are hydrated, wearing the correct PPE. What we really will struggle to do is maintain accuracy in our results. So whenever possible, the panels should be cleaned. So I have another little video of this environment, of where this panel was. So that was our Solar Utility Pro there. This was a 1500 volt site in Southern California. Again, you can see facing some of the similar problems that we had in the UAE. So the question is then, if I'm telling you to clean the panels and you can't do that, what can we do? Well, a couple of things. We can visually check cable connections prior to testing. Okay, so make sure that you walk up and down the system and just give a check on the connections. This is the same for very cold environments, walk up and down the panels, do a visual inspection of the string, make sure that the installation resistance is part of your test regime, okay, and our PV 150 and PV 200 will offer you the installation resistance test, and make sure your instrument is clean. Remember, we said earlier that we should have really solid connections to the array and no dust inside of the connections. So we've done our visual inspection, okay? So what we can do is we could run a test when the panels are dirty, all right? And then we can run them when the panels are clean. And then what we can do, use those two sets of data to show the client how much more energy they will be generating and how much more performance they will get due to the cleaning process. But the big question, and I know a lot of people out there are saying right now, well, it's not really viable for me to clean the panels at all. It's just me, it's my co-worker. We've been stuck in the middle of this field for 3 weeks. There's no chance we can get anyone out to clean the panels. Do you have a solution? Well, fortunately there is, and this can help us kind of maintain accuracy with our results. So what I would like you to do is take a single panel from the array, okay? And you're going to measure that panel when it's soiled. We're going to clean that panel thoroughly. And then we're going to measure the clean panel in the same azimuth and inclination as the other panels. And then we use the clean results against the dirty results, and we can work out a soiling factor. And that's something we can apply to our short circuit current and open circuit voltage calculations when we're transposing them to STC. So another real world example for you here. When I mentioned standard test condition values, this is what the manufacturer states, and generally what the solar industry is working to as a baseline is 1,000 watts per meter squared, 25 degrees Celsius. So if you take a look at the back of a panel, it'll tell you what the STC values are for various things. So in this instance, we're going to look at open circuit voltage, which is VOC at 37.4 VDC, and an ISC of 9 amps, so short circuit current of 9. So I'm here in Fresno, Clovis, California, okay, and we were looking at very high irradiance during the day, but you can see on the panel itself, again with the picture, that we have a lot of dust on the panel. So this extreme condition was not even very hot on this roof, okay, so there's a lot of guys there we needed to keep hydrated, but we had to find a ground fault, and we couldn't find it. And what we thought we would do while we were up there is do some testing to show the client what we can do to prevent it getting so dusty in the future, and that of course does involve cleaning. So let's see. So we expected 37.4. and our expected ISC was 8.1. And I have a little video of this now, and then we'll find out the results.
It is standard test conditions, but which are
1,000 watts is where we was.
Yeah, I know. 25 degrees Celsius. Exactly. So we should see 37.4. So right now on this panel we're reading 33.1 because the temperature is higher, and that's bringing down the VOC.
So right now on
We
this
also
panel
see
we're reading
879 watts per meter squared of irradiance
because
on
the
the panel.
temperature is higher,
So
and that's
if
bringing
we
down the
work that out,
VOC.
so if it's 9
We
and
also
1,000,
see
we should
879
see
watts per meter
at least
squared
8
of
amps
irradiance on
when
the
we run a
panel.
test on this
So
panel.
if we work that out, so
running
if it's
testing,
9 and 1,000, we should see at least 8
So I
amps
see
when we run a test
5.64.
on this panel.
Okay, which
So
is what we were
running
getting before.
testing,
Okay, so now we're going to clean the panel, and we're
so I
going to
see
retest it
5.64.
and leave it for a minute. Just
Okay,
to
which is what we
catch
were
its
getting
breath.
before.
And then
Okay, so now we're going to
we'll
clean the
retest.
panel, and we're going to retest it, and leave it for a minute just to catch its breath, and then we'll retest. Okay, so what you can see there is, I was explaining to the team that we're going to expect 37.4 volts, but due to the extreme temperature that we were under in California at the time, we would expect the VOC to drop. And then we looked at the soiling. I said, okay, well, not taking into account the soiling, if if at 1000 watts per meter squared, we should have seen 9 amps. Then at 900, which we are at now, we should see around about 8. So we also didn't take into account the soiling. So what we did there was we calculated our expected values. And when you're dealing with an extreme temperature or in an extreme condition, really keep these expected values in mind and work them out. So what we measured at the end of the video, we'd actually lost around about 4.4 volts on our VOC, okay, due to the high temperature. And we lost over 30% of our short circuit current, so of our power. So what we're seeing there is we knew what to expect from our instrument because we'd accounted for it via our visual inspection and our expected results. So don't expect your results to be exactly like what the manufacturer said when you're testing in extreme conditions. You have to account for every possible aspect that could be affecting the results, and then you'll better understand what's going wrong with the PV array. So do study the results carefully, and also videos and pictures give great context for clients. But what we did do with this test, because we were at the homeowner's house, we were able to demonstrate to how much energy production they were losing in real terms. So a lot of contributors have helped this presentation so far. So before we close out, I'd like to thank Hamza, Caleb, Marco, and Barry, who all responded to my LinkedIn post. These are great guys, and I thank them for their input. So I put the question out there on LinkedIn. I said, please, can you tell me your experiences in extreme environments, and what do you do to keep your people safe and your instrument working correctly? Well, the feedback I had from those gentlemen I spoke of on the last slide, I'm going to summarize here in these two last slides that we have. So with your personnel, always use well-ventilated light PPE. So I think PPE sometimes is not looked at correctly. You know, there isn't one size fits all. Particularly here in the United States, you could be on a hot site one day and then shipped off to a cold site the next day. So if you're buying your own gear to take to a site and it's not being provided for you, ensure you have the correct equipment for the environment so you can get a fanned PPE that will keep you nice and cool. Ensure everyone is well hydrated. Obviously, that's a no-brainer. Just make sure everyone is well watered. But this was a good one, rotating personnel in the field. So rather than just have one team out there all day working for 8 hours, you know, as they slow during the day and it's very, very hard in the off gear, rotate the personnel every couple of hours to keep them fresh and to keep them well hydrated. This is a good one. To ensure data can be captured quickly from the field. So instead of having to drive back to the main base to download the data and then test again, make sure you have facilities with you to test and download to a laptop or whatever it may be. Always test from a shaded area. So we talked about this as well. So if you can test underneath the table of panels, or you can see in this picture, this is a site in Alabama, an 80 megawatt, where we were testing our Solar Utility Pro as a prototype. You can see the gentleman's testing from underneath the cover of the truck, and that just gives us a little bit of shading for him and also for the device. So that's what we could do with our personnel. With regard to the instrument, store it at room temperature. Okay, this is key. So I've mentioned a couple of times throughout the presentation that if you leave it in a truck overnight and it's very, very cold, it can cause damage to the unit. Similarly, if you leave it in a very hot environment overnight and then begin to use it. So it's better just store it at room temperature whenever you can. And if you're leaving the instrument for a long period of time, then I would suggest removing the batteries. You could also operate from an AC cooled vehicle or shaded area. Okay, so one of the suggestions, I believe this was from was from Cal, was they used extended cables. So you had one person at the combiner box, the other was using very extended cables towards the truck, and he had the AC on in the vehicle. So therefore, you're not exposing the instrument to the very high or very low temperatures. You can see here in this picture, this was another site, but you can see that we actually had the unit out on the top of the combiner box. And I put this picture in as maybe a way of saying this is bad practice, and I shouldn't have done this because I've left the instrument exposed to direct sunlight. It probably would have been better down here in the shade. I mentioned earlier that the temperature probe can fall off, so you put a good bit of tape in your kit bag. Make sure you have that with you, and really do keep the device clean at all times, particularly in these dusty environments. Okay, there is a question coming through, and I will answer all of the questions shortly. We're just on the last slide here before the Q&A session. So I've talked a lot today about testing solar PV, and the instruments I were talking about was the Seaward range. We have a PV150. This is our real workhorse unit. This is 1,000 volts, 15 amps instrument. We'll give you VOC, ISC, continuity of earth, insulation resistance. It also comes with a current clamp. A very, very good unit. Holds a lot of records, a lot of onboard memory. One unit up from that is our 210, which offers the same functionality, but also offers IV curve tracing and a separate installation function. And this is known as the PV200 in Europe and the rest of the world. And then our Solar Utility Pro, you may have seen it in a couple of shots, is rated at 1500 volts, 40 amps. Great instrument that will give you polarity, voltage, current, radiance, cell temperature, and ambient temperature. So all of these instruments are available worldwide. So thanks for your time. I'm going to cover a couple of questions. One from Debin. What's the effect under extreme low temperatures? So very similarly, when we leave the instrument in very low temperature, you can have a buildup of moisture inside of the instrument, which can cause it damage, and the electronics just won't work properly. So we say try to use the device above zero at least, and try and keep it dry. Rowdy has asked, what is the operating temperature of the device? Will it work in normally rough areas such as KSA? So what we have to do, Rowdy, and part of the presentation today was to try and teach a little bit of best practices, that if we just take the unit into an environment without thinking about it, then you will definitely have problems. But when you're working in a rough area, like you said, as KSA, I would suggest store the instrument in indoors overnight at room temperature. Okay, don't put it under direct sunlight. Ensure that all of the connections are not dusty. Work out this shading factor with the panels. Give the unit time to rest in between tests. If you feel it getting hot, operate it from an AC vehicle. So there are different things we can do to mitigate the problems. But the operating temperature of the device is between 0 degrees and 40 degrees Celsius. That's what we state, and that's what our manufacturing specification is. So what I'm trying to do is give people options to help stay within those kind of limits. A question on the Solar Utility Pro, can it do curve tracing? No, it's not a curve tracer. We called it a string checker. So it's giving you the essential commissioning tests, polarity, voltage, short circuit current, along with the radiant, cell temperature, and ambient temperature. We do have access to a 1500 volt curve tracer. Please do contact me if you'd like to hear more on that. Pedro, the presentation will be sent out after the webinar. So thank you. Even when I'm testing, so Rowdy's saying, even when I'm testing, I shouldn't expose it to sunlight. No, that's not what I'm saying, Rowdy. What I'm trying to say is just try and keep it out of direct sunlight. So let me give you an example. So you can see in this test here, we're testing, but we're testing in the shaded area. Okay, so, and also don't kind of get it out of the truck and then leave it on the truck bed, walk away and come back. I'm just kind of saying don't leave it in direct sunlight. So when you're testing, if it's in direct sunlight, that should be fine. Just when you're storing it, when you go for a drink, when you go back to the truck, whatever, don't just leave it lying in the sun, and whenever possible, keep it in a shaded environment. You'll just have a much better time with it, and it'll test more consistently for you. Yusuf has asked, what is the LID loss and how can it be measured? So LID is light-induced degradation, and basically when the modules are manufactured, particularly maybe if it's in China or somewhere that is far away from your location, the panels are flash tested in the factory, and then they're put on a pallet, and then they're sent to maybe Shenzhen or Shanghai, and then they're on a container to wherever they are. So they're not exposed to sunlight from a very long period after the flash test. And then what happens is the panels are put onto the framing system, and they're exposed to LID almost immediately, so they will be generating more than what they will be. So what I would suggest is curve trace as soon as they're installed, take that IV curve, and then curve trace again 2 or 3 days later, and then compare the two, and then you can see what effect LID has had on panels. That's for new installations. For older installations, again, there is the opposite effect. So in the morning, test the system IV curve, and then later on test and get our IV curve and compare the two, and then you should see the LID effect. Okay, a couple more questions coming through. Bart has asked about our ISO on 1500 volt DC systems. You would need a 1500 volt installation tester. Michael Dudek has asked, Michael, great presentation. Can damaged modules be detected by testing? What defects can be detected? Can you test modules with partially cloudy skies? Is it possible to infer the failure of the module based on tests in such suboptimal conditions? Great questions. Yeah, with regard to a damaged panel, if we're looking at IV curve tracing, definitely we would see either micro cracks or apparent in the IV curve trace that we take. And the good thing is we then take that measured curve and we transpose it to STC. So then we can directly compare against what the module manufacturer said the panel should be creating under those conditions. But what I was trying to get across here, Michael, and this comes to with your final question on, is it possible to infer the failure of module based on tests in suboptimal conditions? What we have to do is we try to make those suboptimal conditions as optimal as possible, if that makes sense. So this is where I was talking about clean the modules whenever possible. If you can't clean, ensure you get a soiling correction for your data. Do whatever you can. So I would say soiling is easier to fix than the second part of your question, which is partly cloudy skies, because we can't. That is something we really can't fix. If we get a change in irradiance during the test, that's going to affect current, and you just won't get a good IV curve and or even accurate ISC results. So I hope that answered your question. I didn't go into too much detail because we do have a presentation on IV curve tracing, which we'll be doing in the future, and we'll be sure to invite you to. Okay, a couple more questions coming through, just trying to get through these. What is our ISO? Asked Mohammed. Our ISO is insulation resistance. Good day, Mr. Michael. Any experiences of the device detecting improvements to VOC and ISC in a solar tracker powering plant as compared to fixed tilt? The reason I'm asking is because we'd like to use the data as a marketing point. Yes, Ashwin, definitely. You would be able to track that. You would go and take a result at one point in the day, let the tracker move, take another result. And again, we could just layer the IV curves on top of each other, and you can see a real great improvement in performance demonstrated that way. Yusuf has asked, could you please illustrate potentially induced degradation? This presentation isn't on PID, Yusuf. However, I can give a brief explanation. over time, the photovoltaic effect of a panel is degraded due to the potential for the energy to escape into the framing system, and over time that lowers the VOC. So that's a brief explanation, but PID is a very good subject and one we do cover in the IV curve tracing presentation. Does the Solar Utility Pro equipment do IV curves, or do we need another tracer? Yeah, it's not an IV curve tracer. It's a real workhorse unit. It's a string checker, so you could check an entire PV field with the Solar Utility Pro very quickly. It doesn't need a laptop to operate. It'll give you VOC, ISC, it'll check polarity, but it won't do the curve trace. So what I'm advising, if you don't need to curve trace the entire site, then don't. You know, it's a lot less data to handle, and so you could use something like the PVA 1500 from Solmetric to get the curves, which we also have available, and the Solar Utility Pro to get the other items. I have another question here. What is the difference between choosing independent or parallel connection MPPTs, and which is better? I think if you're talking about paralleled connections, I mean, the difficulty is the PV150 and PV200 are rated at 15 amps. So if you parallel two or more strings, you know, we're going to be doubling, tripling the amperage, which makes it harder to test. Okay, so from a testing perspective, parallel strings are worse. From a design perspective, they're much better because we can parallel, you know, 10, 20 strings into a single fuse holder, have fewer combiners, have fewer fuses. So from a design perspective, parallel strings are good. From a testing perspective, they're bad. So just really be aware of what you're connecting to. Nice, easy, you know, single strings into one part of the MPPT each is easy, nice to work with. But again, on larger systems, you're never going to get that type of design. Okay, so I don't see, oh, one more question. Javier has asked, in the case of parallel strings, is it valid to make the test on the string box side, or do we need to test both separately? I would ask that question to your client. So, you know, solar testing, there is, you know, the IEC standard, the UL standard, or really a lot of it, particularly in performance verification, is what does the client want to see? So in the case of parallel strings, you ask, is it valid to make the test on the string box side, or do we need to test both separately? I would ask the client, do you want me to test all of these in parallel, or do you want to see each string individually? If I test them all individually, it's going to cost you X. If I do them in parallel, it's going to cost you Y. In parallel, you should still be able to pick up errors. So voltage errors might be more difficult. They'll be masked, but certainly, you know, current, we can still calculate what our expected values were. But then if you do find that your measured value is not near your expected value, then you have to localize it to one of the two strings anyway. So it's just, you know, if it is down to you rather than the client, then test out a couple of methods of working and see which one works best for you. I don't like parallel strings because they blow up our units. So that's why the Solar Utility Pro is so good, because it's rated at 40 amps. So Rizwan asks a question. I have a question regarding selection of Seaward instrument for use on 1500 volt DC systems because I couldn't find any compatible device on your website. Rizwan, we have a great instrument available, our Solar Utility Pro. We also are able to offer the Solmetric IV curve tracing device. Oh, Rizwan, if you'd like an IV curve tracer, please get in touch. My email is michaelm@seaward.com. So Michael has asked, what's light-induced degradation? Michael, I don't profess to be an expert in the subject of LID, but my understanding is that when the panels are flash tested in the factory, they're then sealed, and then they don't see sunlight for maybe several weeks or several months until they are put out in the field. And at that point, the photovoltaic effect is activated for the first time in a long time. And I guess the term is it's hyperactivated, and they generate maybe 5 to 10% more energy than what they normally would. So what happens is the light-induced degradation kicks in and it brings the panels back to their steady level of generation. That's my understanding of LID on new systems. Okay, well, I'd like to thank everyone for their time today. I got one more question here from Rehan. Excellent presentation, Michael. Thank you. That's very kind of you. It's the first time presenting this, so apologies for the stutters. Is it possible to check subpar panels based on the PV150 and PV200? Absolutely. So what we would do is we just, as I mentioned earlier, we take our expected values, and we compare them to our measured values, and then we can see what the difference is. I have a whole presentation on fault finding with the PV150 and PV200, Rehan, and I'll make a note that we'll get that out to you as well. So I don't see any more questions coming through, but I'd like to thank you all for joining me today. If you want any more advice on solar PV testing, or you would like to inquire about the price of our instruments and where you can find them, both here in the US, in Europe, and in Asia, then please do get in touch. My email is michaelm@seaward.com. You can also contact sales@seaward.co.uk. That's sales@seaward.co.uk. We will follow up with a presentation, a copy of the presentation rather, and the video upload for everyone that attended. So thank you.